All right, great. Thank you for having me. And hello, everyone. Okay. All right, very good. Yeah, so I want this lecture. Yeah, I'm here. I'm actually alive, like live in front of you. So feel free to ask any questions as I go along. And this is a small group, so it's nice. Okay, so feel very comfortable just asking questions. So I was tasked here with giving a lecture on artificial matrices, and I teach a course, tissue engineering, principles of tissue engineering, there at NGIT, and so so some of this comes from there because a lot of that field, broader field of tissue engineering, regenerative medicine uses these scaffolds or matrices. So I'll teach from that perspective, but also teach from the perspective of what are artificial matrices? Why do we use them as good in vitro models, right? Or part of an in vitro model to grow cells or look at cells and things like that. Okay, so what you've been learning already, so I can kind of skip through this pretty fast, is the extracellular matrix, okay, that cells interface with, right? Will dictate their function, okay, to some degree, right? And so animal cells, shown here, whether they're these epithelial-like cells or these mesenchymal cells, will interface with that surrounding matrix, okay, whether it's kind of this dense basal laminae, or if it's mesenchymal, they're in this loose connective tissue-like matrix, okay, but that's what they're interfacing with. And the plant cells, again, have this kind of organized, also their cell wall is that what we consider to be that matrix. So as engineers, we try to imitate that, right, in either a culture environment, or if we're developing a therapeutic strategy, that's that scaffold material that we're going to deliver the cells on. And so if we look very carefully at it, if we try to imitate it, mimic it, it's pretty complex, yeah? So, this is kind of a higher, mag of that. And so, animal cells may be interfacing with, well, you think just native collagen maybe. Collagen makes up a lot of the tissue matrix. But there's all kinds of other stuff around that collagen, proteoglycans, laminins, okay? And it's organized, or the structure, physical structures at very different length scales, right? And what's shown here is more nanoscale types of features. But it can even organize, those features can organize into larger microscale types of structures, right? So you have to kind of decide, what am I going to be looking at? Nanoscale features, microscale, how am I going to imitate some of those physical structures? And then maybe some of that chemistry. So same with the plant cells. Different scales, right, of structures, different chemistries. And okay, and so over the years then, we've gained a lot of understanding of what those matrices are, what compositions really affect cells significantly, and we put that then or have engineered these artificial matrices for different technologies, right? And so tissue engineering we use them a lot. This is kind of that first product that was developed by Apligraph, or called Apligraph by Organogenesis. That's a collagen matrix. Skin cells are on that's for skin repair. But more recently and more, I'd say over the past decade or so, more for drug development. So we're using these matrices in culture dishes as maybe high throughput screening, or could be on a smaller scale, but they're three-dimensional in vitro model systems where you can put cancer cells or other cell types on and try to figure out what kinds of drugs, right, you could use or develop that may kill the cells, or if there are other types of cells, make the cells thrive and behave normally. So very important. So these types of, again, matrices are what we can consider to be artificial. They can be derived from natural materials, okay, natural, which I'll jump into, but or they can be derived from synthetic materials, okay? And so I wanted to kind of run through some of those compositions with you so you can get a sense for kind of the pros and cons of those material compositions, and so why people use these and why do they use this versus why do they use that. Okay, so you can kind of have a better understanding of that. So when we get into choosing materials for those types of applications, again, you're trying to figure out compositions or actual designs when you get to a higher level and actually producing the scaffolds or matrices, so that, again, you can get a desirable cell response, whatever that cell response is, okay, at either the single cell level or maybe it's a group of cells, right? So you either trying to look at just single cell interaction with the ECM, or maybe it's tissue growth that you're trying to form in this kind of 3D environment. So cells need to interact with each other. They also need to interface with the ECM. And that matrix becomes even more important because you got to get good nutrient transport and support to keep the cells alive if you're getting really 3D in these structures. So things that we think about as engineers and trying to put these things into dishes and make sure that you can have a good amount of these things and be able to process it is just this, right? So these biomaterials, we need to be able to process them or even manufacture them if we need to get to that level, right? If you're actually developing a product out of this, okay, that you're going to sell, you need to be able to manufacture it. So, but on a smaller scale in the lab, you need to be able to process it. So you got to choose some materials that you can be able to process, and you need a good amount of them, and be able to form that final design, whatever that final design is. So it's a part of the challenge in processing that you face here. Well, you could say, and this is more of I'll ask you guys, you could say, well, we're trying to imitate the tissue, okay, the native tissue. Why not just use native tissue in a dish? Why not do that? Anybody have any idea? Why not just put, if I want to look at bone cells on bone, okay, bone cells in their matrix, why not just get bone and put it in a dish? Price is a issue potentially. Why would price be a factor? Why would it be costly? Okay, so yeah, you got to buy tissue, right? So it's got to come from somewhere, a donor. Maybe it's an animal source or something like that. But you do have to buy it, and usually it may not be that accessible, right? So price is going to actually drive up because the supply is going to be limited. So price is a factor. What else? Okay, so it's not living anymore, but that's okay. We can maybe put cells on it, and we can take tissue and decellularize it, and that's probably what we want, right? Because we want to have that matrix around it. Maybe take the cells out. That's okay. We'll put cells back in. But maybe there's some...
Depending on the final application, like you want to move this to humans, you have to think about immune response, so the source of that tissue.
That source of the tissue. You could have immune response. So that's an additional factor that you're going to have in your culture. And we just don't know what the impact might be. So that could be an issue. Maybe one more.
Donor variability. So
that's a big one. Yeah. Yes.
Materials from different animals, it's harder to control the composition of that tissue.
That's right. That's right. Yeah. So yeah, you need a good amount of this stuff. Where are you going to get it? You can't get it all from one animal. So yeah, you need a lot of animals, and they could have variation. They could be old, young, disease, whatever, right? So a lot of variation. And then also the composition itself, right? I already showed you there's a lot of different types of stuff in that matrix, right? And so if you're trying to understand how the cell is behaving with those extracellular matrix molecules, when it becomes very complex like that, how do you tease out which thing is acting on this part of the cell? So a lot of times you do want a single chemistry in your culture. So that's another reason that you want to have a well-designed, reproducible type of matrix. Okay, and the big one is sufficient quantity, and you pretty much kind of said that. You need a lot of this stuff. You put it through, you need a lot of it. So taking it again from animals and keeping that structure there can be tricky and have to have a lot of that. Okay, so again, that's a big thing. And then suitable mechanic, whatever, when you fabricate this stuff, retaining, or figuring out what kinds of physical, chemical properties, mechanical properties that you want in the matrix. That can be tricky, right? Because you need to figure out, again, with your processing, you can lose a lot of that. But it's, again, developing processes that can maybe give you that or retain some of that. And then hopefully you don't want to kill your cells, okay? Maybe if it's cancer stuff, maybe you do, but you don't want to kill your cells. So your materials, after you process them, need to be not toxic. Okay, so what materials are we talking about when we put these things in when we're designing? What compositions are we looking at? So like I said, you can use naturally derived materials, or you can use synthetic materials. So I'm going to kind of start out just going through some of those natural materials. And I just put up a big table, but I'm only going to highlight a few of them that are routinely used, okay? So we'll start with natural materials, then we'll go into synthetic materials, and then we'll try to culminate things by looking at a couple of different processes that people use to fabricate the scaffold. So we talk about natural materials. Again, this is a big list. So these tables, this stuff comes out of this big Bible textbook of principles of tissue engineering. Okay, so these tables come out of that. So here's a list, right, of natural materials that people have worked with or are commercially available. And at the top of the list, right, and maybe because of alphabetical, well, maybe not, but at the top of the list, really, because it is used a lot, whether it's as in therapeutic or in vitro, is collagen, okay, and gelatin, right? Okay, and again, why? We'll get into that in more detail. But again, having a good amount of this stuff is important. Okay, be able to process it and develop, like I said, all of these technologies. So you can get it from various sources, which is important, and you can process it reasonably well, depending upon your application. So it's used for a lot of different applications and studying, but again, because collagen is kind of that main protein in your tissues, that one's readily used. So we'll dive into that. But there's a few others, right? There's elastin, keratin. These may be more specific to certain tissue types. Silk, which comes from insects, okay? Proteoglycans. These things have been isolated and have been processed into different types of forms. Again, depending on maybe the mechanical properties that you want or the specific tissues that you're looking at, these may be more favorable as a composition. Silk is mostly used because of its strength, right? And it forms these very nice fibers. You can form these fiber structures. Proteoglycans, we'll talk about the glycosamido-glycans that are part of those proteoglycan structures we'll talk about. And then you've got other plant-derived, more plant-derived or other types of derived materials. Cellulose we'll talk about, and very abundant material, okay, and somewhat still limited in its use, but we'll talk about that. And then there's others. The starch, alginates, like I said, the Gags, which are part of the proteoglycans. Again, major, readily available. All these are kind of readily available types of materials. So we'll get into these. These have different properties than, say, your collagen or protein. So we'll talk about why they may be more favorable for certain applications. And then the chitin chitosan. Okay, so fairly good amount of natural materials. So if we start going through some of them, like I said, the major ones that I'll talk about then, and just as a little bit of background, I guess, with the proteins before I jump into that. Again, when we talk about proteins or peptides, or these peptide bonds. So in proteins, what makes them stable, okay, even in the body, is these peptide bonds or amide bonds, right? And all that's great, okay? All that's great in the body, but when we try to isolate that protein and then try to process it, that becomes our problem again. Why? Because it's a very stable bond. So it's a very, what we call hydrolytically stable bond. So when we put this stuff in water, it doesn't dissolve, okay? And because of that, then we have to really use other more challenging organic solvents. And when we do that, the stuff starts to degrade, okay, or denature. So that can be a real problem, right? And so that's kind of the major shortcomings when we're talking about, in general, proteins, okay? It's the processing and trying to maintain that structure. But naturally or normally in the body, those materials will degrade by enzymes. And all that's fine. Okay, that's fine. So that's a major shortcoming. Processing. So can't really use water to kind of dissolve this stuff. You also, heat is a problem, right? So conventional processing methods, which sometimes require heat, okay, will denature these proteins, and then you're left with whatever you have. And then you have also, there is possibility, again, these are kind of animal-derived, or could be human-derived. There can be some mild immune response or immunogenicity. And that's usually, you're going to find that more if you try to implant, if you're implanting these materials. So people have found that there can be, if using bovine materials, there can be antibodies built up for bovine. Not really clear what that means, but people will produce antibodies against it. Okay, proteins and peptides, other things. Again, when you start to really process these materials, you do lose mechanical properties, or can lose some of their, favorable mechanical properties. So again, you have to kind of think about how can you modify your process to hopefully recover some of that. But clearly, the benefits in many cases outweigh those drawbacks, right? You eventually just come up with your process, develop it, and tailor the mechanical properties to what you want for your system. And then you've got your nice proteins in your culture. And as you guys have been learning, there's these huge biological properties that these proteins have. So the cells are binding directly to those materials. And whereas some other synthetic materials, you don't see that. You're not going to see that behavior. Okay. So when we talk, collagen, right? So collagen is widely used, right? Like I said, as a scaffolding material, either for implantation or in vitro. It's in all of your tissues, or many of your tissues, so 30% protein. Collagen fibers, okay, are really mechanically strong, right? So the modulus kind of shown here, and yield strength and strain, all these things that you guys have been learning, properties, relatively high, okay, relatively high. And there's various types of collagen. Type 1 is really the most common, okay? And when we talk about properties in terms of fiber properties, mechanical properties, we're really talking about the type 1 collagen. And again, that peptide structure there, amino acid sequence and things like that are in collagen really gives it very nice biological properties, which we'll talk about. Okay, and so again, easy to isolate and get from sources. Just a little bit on the chemistry, and again, why I just mentioned this slightly only is because, again, it becomes the challenge with collagen is that, it forms this nice triple helix structure, okay, and so this 3 left-handed helix, and then these 3 left-handed helices that then form this right-handed helix. It's got this, like I said, repeating peptide sequence, mostly this glycine that's present that kind of keeps repeating through the structure. Fairly long chain of these amino acids. Okay, and like I said, it's produced by the cell. It's produced by the cells. Skip over this a little bit. okay? And so, like I said, the advantage here is that amino acid sequence, okay, and that helical structure. So the cells are binding to those various types of the various amino acids that are present, right, in that structure, and via these integrins. And what happens then, right? So as you begin to process this material, okay, usually, like I said, it's not soluble in water. So what happens is you may use acids, okay, and sometimes, you know, it just depends. You may have to use some strong acids, but you're generally going to be using some acids, and then you're going to have to kind of bring it back up to its pH. The collagen will spontaneously polymerize, but you will lose that, or in many cases may lose a lot of that helical structure, right? So you're losing a lot of that hydrogen bond that's happening between those polymer chains. It will polymerize again, but you'll have less of that present. Okay, so if you isolate that collagen, say it's coming from rat tail tendon or tendon types of, which is a common way of isolating collagen. You use a lot of it, okay, but what you actually recover in terms of collagen fibrils is not that much, right? So you lose a lot of that ability to be able to come back as a collagen molecule. So you can create collagen gels, and strength is very weak, right? And those gels are usually not stable, right? So you'll kind of get this dispersion of fibrils in the gel, but you have to cross-link, right, to be able to try to get some additional strength in those materials. So you're basically forming chemical bonds or covalent bonds between those polymer chains in order to kind of strengthen the network that you formed here. And so when you put the cross-linking in, you may have to heavily cross-link it to get to any suitable mechanical properties for what you're trying to do. And also that will help reduce it from being soluble. So it will decrease or increase the rate of or degradation time. So you have much longer time for it to sit and be stable. The reduced capacity to absorb water, and then, like I said, increased mechanical properties. So that's, pretty much the drawback there with collagen is that, like I said, you lose some of its favorable, ability to be able to form these fibrils naturally, and you have to put in a lot of heavy cross-linking. But what you're still left with is still a functional, you can still have a biologically functional type of protein. And you've got these free amines that are present also that you can bind other types of molecules to, which is also beneficial. So in terms of attachment, there's some, people have been discovering then what sorts of peptide sequences or amino acid sequences are there, peptide domains. So integrins will bind then to these different structures in collagen pretty readily, and so that's good. So that, again, you interface, and basically you're doing exactly what the cells will do in the body. And so very well studied, cells will attach and behave normally. So the phenotypes of these cells remain the same. And so again, these are just kind of examples, fibroblasts, chondrocytes, things like that. Okay, and so again, collagen will degrade via these enzymes in the body. And then, like I said, we will process collagen. If those gels can be highly cross-linked, that will give you a stable, material in culture. Or you may freeze dry, okay, these materials and form like a porous sponge, and which I'll show down the road. Okay, and that's another way. And so you you dehydrate it. Okay, that actually helps to stabilize it again to some degree, and then you can form. In a dried form, you can form these sponges. Okay. So wide application use, like I said, translational use. They will combine collagen with other materials for, say, skin repair, or blend them with other synthetic materials, okay? And again, that will help to improve mechanical properties, which my group has actually been doing. And then we also can apply active factors to it. Okay, and like I said, that's the product on the market using those types of matrices. So collagen is collagen, right? So that's like that fibrous protein, and it may be suitable for cells that, mesenchymal cells that you want attached to that type of matrix. You may want to look at other materials, okay? Polysaccharides, which sugars, right? These long-chain sugars. And polysaccharides play a different role, right? A slightly different role. We're actually not that clear on the role, I would say, the biological role. But depending on some of their chemistry, which will show neat things can happen. You can put, again, different growth factors or proteins will attach to those materials, and then cells will behave. But proteoglycans are these long sugars, and okay, and so there's a number of natural polysaccharides that are embedded throughout your extracellular matrix. Okay, and so in plants, you've got the cellulose, okay? This is a relatively simple, right? Simple structure here. So you've got these glucose units or monomer units that basically build this structure. And very tough. It's a fibrous material. And so you can get it from cotton, wood, things like that, okay? So we will also work with this material, and we modify it. Why we modify the chemistry slightly is because this big limitation, it's not biodegradable, and it's not soluble, okay, in water. Again, it's this water issue, right? So if we want to process it, again, the water problem comes up. And so, again, what we do, we'll modify and make it soluble. And so what's available on the market are some of these derivatives or these modifications. So you add some different groups here, okay, to the cellulose chain, and then it becomes water soluble, and then you can process it. Okay, but again, it's very beneficial. Why? Because it is natively fibrous material, and like I said, very tough, very strong material. So in many ways, people are looking at it as a substitute maybe for collagen, if you can modify it to have some real biological benefit. Okay, so that's cellulose. And then there's the broad class of the kind of animal-derived or native gags that are sitting in your body. So the mammalian gags, the glycosaminoglycans. And so again, these are sugars. Again, these monomer kind of units vary depending on the type of gag that you have. So you may have what's shown there, the uronic acid and this amino sugar. And depending on the type of composition you have. And again, what happens with these materials, you may, in this case, the hyaluronic acid, you have an overall more negatively charged material here. And so a more negatively charged material electrostatically will actually interact with positively charged proteins, and those proteins, okay, may be beneficial. Okay, and so these materials, some of the other types of gags may be bound to a core protein or makes the larger structure, the proteoglycan. Okay, but these materials, like I said, depending on the type of charge they have, may interact, like I said, with these proteins and then impose a biological function. They also can hydrate, and so when they hydrate, then they can be used also mechanically, okay, to apply. So a lot of these gags are in cartilage, so cartilage can withstand high, compressive forces. So that ability to be able to hydrate, absorb, and hold water, become a nice hydrogel becomes important. So those materials can do that. Okay, so hyaluronic acid is kind of a more popular one. or hyaluronin. That's commercially, again, available. It's used really a lot for cartilage, but it can be processed in different ways. It can be a viscous fluid solution, or it can be cross-linked to form hydrogel, or even a more solid material where you can create membranes, particles, and things like that. And very mild, no foreign bioresponse, and then again, enzymes will degrade the material. Yes?
Question. So hyaluronic acid is, if you look it up on the internet, everything you get is a cosmetic.
Yeah.
And it's widely used in cosmetic applications. So where does that come from?
That hyaluronic acid? Yeah. So the cosmetic ones, I'm not 100% sure, but it could come from, so the natural one is these rooster combs, right? But you can also more synthetic or semi-synthetically make it, right? So this microbial fermentation, you can do it that way. But so I'm thinking the cosmetic one probably comes from the microbial method. But the stuff they inject into the knee is that rooster comb derived stuff. Yeah. So, and again, there's no immune response. Okay. So, yeah, the only real issues with the hyaluronic acid, like I said, is, and this actually may be beneficial for in vitro culture, is that it does degrade really slowly, okay? And so that's nice, right? In vitro culture, if you want to study cells for a long time, that's okay. You can keep it there and it'll be pretty stable. More translationally, again, if you want it to resorb fast, that may be a little bit of a problem, but it depends on the application. And again, limited range of mechanical properties. Right. So again, still not really clearly understood how hyaluronic acid works biologically. Like I said, in many cases, for cartilage anyway, it's acting as a lubricant because that's kind of hydrogel cartilage that you have. In terms of its, it may be used as an encapsulating material for cells. And generally, the cells may or may not be interacting with it unless you kind of modify the hyaluronic acid. So in the body, like I said, it's not that clear what its biological function is. But there are materials out in the market, as shown here. This is for wound healing, Hyalomatrix that's out there. And that's more about like a fibrous solid device. So these other materials then, there's chitosan, which is very popular. And this is more, I would say, as an in vitro culture type of material. But although it's being investigated slowly, clinically. Again, derived from chitin. And it is positively charged material, shown here. Okay, and again, and then I'm just running through this a little bit. The chitosan, beneficial thing about chitosan, it again is biodegradable, and that lysozyme will actually break down the material. It can be modified again, so you can create, again, and cross-link and do different things to create solid structures, which is good. But again, you really have to modify the chitosan. Again, there's no really way of cells to, by itself, bind to this material. So there isn't anything in the structure for the cells to really interact with. Again, you have to modify, add additional proteins or peptides to the material to make it biologically relevant. Okay. Other ones, alginate. Also kind of common, hydrogels are made out of the alginate. You can cross-link these pretty easily using calcium. Very simple method, keeps it relatively stable. And again, it's just that, a hydrogel that you can kind of suspend your cells in. Again, you have to modify it with some peptides if you want to get some adhesion out of the cells, or again, adding some additional factors to it. Very mild response to the material. Like I said, mostly used, I'd say, in vitro so far in some development. Okay, I'm going to stick to that. Okay, so those are kind of the common natural materials. In terms of synthetic, we'll shift to synthetic materials. I'll start a little bit with ceramics, and tell you why I'm talking about ceramics, and then some of these polymers. And when we look at why do we care about ceramic materials, if we're trying to imitate anything related to bone, that type of composition, so you have that matrix is not only collagen, but it also has apatite in there. So it's about 60% apatite, hydroxyapatite ceramic. And so if you're looking at response of bone cells to the matrix, a lot of times you want to include maybe this apatite. And so there's a lot of different types of ceramics out there. You can make apatite in vitro. You can kind of precipitate it, right, in culture. That's one way, and kind of nucleate. There are people that will nucleate it on the collagen fibrils, and there's ways to do that. Or you can, just get ceramics, so buy your ceramic, purchase a ceramic, or you can synthesize some of these other ceramics that are available. So common ceramic materials are hydroxyapatite, and so that imitates the hydroxyapatite in bone. And then there's other ones, tricalcium phosphate, which is a fast resorbable kind of ceramic. So not quite the same chemistry, right? But it degrades fast. So if that's something you need, then that's another way. And it puts calcium phosphate source into your surrounding environment. Bioactive glass, also fast degrading or faster degrading material. And again, depends on what you're looking for. And so advantage again of ceramics and what bone does is that it has a direct chemical, it's called bioactive in terms of chemistry, it has a direct chemical bond, it forms a direct chemical bond with bone tissue, these materials. And so that helps cells to then attach, proteins will attach, specific proteins like fibronectin will anchor down onto those apatites, and then you get cells to attach to the ceramic. So the hydroxyapatite, kind of show they're very complex. These are ceramics, so you've got ionic bonds, very strong bonds, right? And so the major one is kind of this calcium that's interfacing with the hydroxyl group there. So that keeps hydroxyapatite very stable. Okay, so it really does not degrade over time, or very, very slowly. And because of that level of interaction, and I'm going to skip through that a little bit. And, and so that's okay. So different from polymer structures, right? Ceramics, because of that high, that strong bond, ionic bonding, you're really, in order to be able to process them, you're going to be heating these things up to very high temperatures, right? And so you melt them, and then you can create different types of structures or shapes out of those. And so you may have particles, okay, or you may create these porous scaffold blocks out of them. Okay, but it requires high temperature processing to be able to do that. Very biocompatible. Mechanical properties, if you're, again, people will use it as composites. So you're not going to be necessarily using the ceramic by itself unless you want very different. Ceramic, Young's modulus is going to be very high relative to, say, bone. But if you make it into a composite with other polymer materials, then you lower that modulus. And so that's what people will do if you want to really imitate bone tissue matrix. So the hydroxyapatite that you can make or buy is going to be very, very stable, which is good, like I said, good for an in vitro environment if you want to keep it for a long time. If you want materials that will degrade, give you a little more calcium phosphate source in your surrounding medium, these would be better choices. And the beta calcium, tricalcium phosphate, also heated up to high temperatures, make into these porous structures, but resorbs relatively quickly. Okay, so it'll fully degrade in about 3 months, and okay, and it's, you know, like I said, will absorb. It's very hydrophilic. Will pull up cells, and things will attach to it readily. Easy to process. And the glass is also relatively hydrophilic. They are amorphous structures, so they're glass, right? So you've got these ions and a silicon network kind of embedded in the structure, right? So these ions come out readily. So you've got, you know, sodium and calcium and phosphorus. Silica makes up the network. These guys are the ions kind of embedded in there. That stuff dissolves. You put it in solution, it will dissolve. But the neat thing about the glass is that it forms this apatite very quickly. So it is the bone apatite that it forms on the surface when it starts dissolving away. And that's a benefit, right? So you can recreate bone apatite by using this kind of glass in culture. And then you can see all these types of nice biological response that's in that cartoon there, okay, to form bone. I'm looking at my time here, okay. Any questions up to this point? And then I'm just going to race through a little bit more of this, some of the synthetic materials, and then talk about some of the processes. You guys have any questions up to this point? Say it again?
What's considered a ceramic?
What's considered a ceramic? That's a good question. So what makes a ceramic? What's the difference between, and you guys might know, but some of you guys, I'm looking at my student over here. I don't want to put this spot. What's the difference between a polymer, a ceramic, and a metal? Does anybody know? Go ahead. In what material?
So metal is ceramic.
Okay, so what kinds of bonds are in these different classes of materials? And that'll help you define it, yeah.
So, like ceramics are ionic bonds, right? So they have like two different.
Yeah, it's ionic bond.
Yeah, and then metals are metallic bonds, and polymers are the covalent.
Covalent bonds, you got it. So that makes, right? So that's the difference. So your ceramics have ionic bonds. They are very strong these ionic bonds, and that's it. Yeah, salts. Yeah. These are salt. These are really considered, right? If you make up this glass here, these are silica. These are all, oxides. Okay, these all have ionic bonds. And that's it. Okay. Okay. So good. Okay, so the synthetic polymers then. Synthetic polymers. So some of them, yes. So, okay. So I'll just focus on really the main ones that people are really using, I would say, and kind of I have some other ones thrown in there, but that's more relevant, I say, the tissue engineering stuff. The main challenge with some of the synthetic polymers, well, this limitation here on the top bullet is really for translational purposes, right? So for tissue engineering, because you have to go through FDA and all that for these. If you start creating new polymers, you have to be able to show that they're going to be biocompatible. And so there's a limited number of those that are actually available on the market for clinical use, right? So that's kind of that limitation. And so much of what we use, even in vitro, comes from things that have been FDA approved for some time now, and really for decades, okay? And so those are the ones you kind of see all the time. But people are developing new ones. But it's a slow process, and so many are developing these new ones for translation, for clinical use. Okay, and so they have to go through this kind of, process of development and then testing and all these things. But usually, so these polymers are new polymers, or what's the really overarching nice thing about synthetic materials is that you can tailor, depending on the chemistry, a lot of these things, degradation rate, physiochemical properties, so mechanical properties. Okay, much easier than natural materials. And so that's really the benefit of the synthetic materials, being able to tailor your properties. Okay, so the number one polymers that are, or class of polymers that are out there are these aliphatic polyesters. And, right, or these polyalpha hydroxy acids. And so the glycolic, lactic, and the caproic acid, that polymers that are formed from them. And so those have been on the market for quite some time. They're sutures. Originally, they was used as foam pins. And so we have a very good understanding of their properties and how to process them and things like that. And degradation, relatively well defined in terms of the rate of degradation and how it happens. And so with these types of synthetics, you generally are going to have a hydrolysis phenomenon. So you can, water will actually break down this, material, and you slowly get lower and lower molecular weight, and then you get eventually cells. Once it becomes small enough, cells will then take over and kind of engulf the material. And so that's useful. And so we can have different chemistries that we know, depending on our application, if we want to have different ranges of degradation. You may want a very stable material that will last a long time in culture, or something, if it's more for application in vivo, then we may want to have something that degrades quickly. But again, these materials we can process easily. All the kind of conventional techniques that we use for polymer processing can be used. Heat treatment or extrusion, solvent, use of organic solvents, spin casting things. So wide variety of different structures can be made. And if you're not so happy with some of the basic properties or physical, chemical properties of the materials, you can add, blend in other materials easily into those polymers. So you'll see blends and composites readily used. And again, these are used in tissue engineering on the market as products. Again, these transite and dermograph use, variations of these polyesters. So the transite and dermograph this one company, it used to be, originally it was a company, Advanced Tissue Sciences, and now this company's kind of purchased the product dermograph and transite. So these are available.
So does that eliminate the need for other skin, usually the graphs have to cut it off somewhere else and put it on?
Yeah, so it is a replacement for skin graft. Yes. Mm-hmm. And so they're using synthetic materials for that. And again, but the cells really are the cells are doing a lot of work, right? A lot of the work. So it's really there as a kind of a carrier structure for the cells. Again, to lay down their tissue, it will resorb over time. But the cells are really pushing that along, the fibroblasts that they have. So again, what are these chemistries really quickly? So the polyglycolic acid shown there, and fairly simple structure. It's highly crystalline, or so has a highly organized kind of polymer chain network. Which is, fine. The melting temperature is relatively high, but again, what makes this polyglycolic acid nice is that it resorbs fast. So it degrades 2 to 4 weeks, and as you just make the polymer structure larger, it becomes more stable. So this is more, the polylactic acid is a more hydrophobic material. So it will degrade, but it's really slow. Maybe it's a year out or so, or plus. And so again, depends on your application. So you can make, what you see usually are going to be blends. You can have blends of this stuff or copolymers of this stuff where you change the basic unit there in the polymer chain between glycolic and lactic acid. You can have different ratios that will change, and that's fairly well studied. I would say very well studied. How that alters degradation rates and some of the other types of mechanical properties, physical properties. You can have different forms of the polylactic acid. Most people are using, if they want fast degradation, faster, this DL, which is more of an amorphous form. You can have the L form, which is going to be, oh no, I don't have that. Sorry, I'm going the wrong way here. Or this L form, which is going to be, most people will use this because the degradation product is this L-lactic acid, which is naturally occurring in the body. So the LPLA, very stable, usually made into different structures. Skip through that. And again, it was used as bone pins some time ago, but really the bone pins as a bone, what they find is that PLLA as a bulk material, as it starts degrading, it continues to degrade for a long period of time, but you still continue to get somewhat of a immune or adverse immune response surrounding the material. So this is the PLA, polylactic acid, labeled I or implant, and then this is the tissue that's kind of surrounding it. So you got a lot of kind of fibroblasts and macrophages just hanging there around that material, not really forming, tissue up against it. You want bone in this case up against the tissue, but you're not really getting that, right? Because you're getting this lactic dump of lactic acid, constant dump of lactic acid in the environment. So that's always been the challenge with that material, especially in bulk form like that, where it's a solid implant. When it's made into scaffolding and very porous, doesn't pose that much of a problem in terms of degradation. The PCL, polycaprolactone, this one's probably has really kind of come up, I would say, over the years, and maybe becoming on a number one material in a lot of the academic labs for use in culture and for clinical application. And why? Because, again, it's relatively easily to get your hands on. It's cheap, but also it has some additional unique properties. It's very similar to the other ones, the PLGA, overall really PLA, and it's stable for a long period of time. So this stuff will degrade over a period of 1 to 2 years. So again, if you want a stable polymer in your culture, this one's a good one. And you don't have that acidic byproduct breakdown also happening in your culture. So that's a big plus with the polycaprolactone. And mechanically, it's easier to handle. So it has a very low glass transition temperature. It just means at room temperature, even body temperature, it's rubbery or flexible, right? So, and so that's also neat. And it has a low melting temperature. So again, if your process dictates, depending on what you're trying to use, maybe lower temperatures, that's also a good one to use for that. So this PCL is widely used because of these kind of properties here. And then you can make different structures and things, very biocompatible. Okay, losing my time here. So I'm going to skip over some of this stuff. More or less, these other synthetic materials are kind of materials that are in development or are being used, but maybe in this case, maybe this is for more drug delivery. They have fairly fast degradation rates, or some are, again, just early stages of development. Polyurethanes are kind of coming up and becoming very popular because these have very neat properties, mechanical properties, and they can, they're relatively they're kind of temperature sensitive, so they can change shape. They have shape. They can be designed so they have shape memory types of properties. So you can kind of mold them, and then they'll expand back and things like that if you want to insert them into different defects. So that polyurethane has become of interest. I'm just skipping through some of these other ones. And for that, okay. So just get down to this, the last one here, some of these other last slides here. So again, just to kind of summarize a little bit, like I said, so you have these different types of materials that you can use. The most, in terms of developing them as scaffold matrices, like I said, the number one thing, and I've been repeating and talking about, is being able to process them. And then also, like I said, but it's choosing also chemistries that will work for you for your application. So if it's mechanical properties that you're considering, then you have to decide which ones give you those suitable mechanical properties. Or it's certain chemistries, then that is also the issue. In terms of fabrication, so I'm going to quickly just run through this a little bit. So there's a number of processes that you can use, and they've been out for a long time. A lot of it has been adapted to kind of matrix or scaffolding technology. And so many of these materials, you want to form a structure that, like I said, will allow your cells to be able to grow or interact right with that structure. And so in many cases, when you start to build large 3D structures, not only do you have to make sure, it's of a certain dimension maybe for your cells to interact well with it, but you also have to, which is kind of this stuff, growth and, all the cell behaviors that you want. But you also have to take into account those structures need to provide this kind of adequate nutrient and gas transport in culture, or if it's in the body for blood vessel formation. So the pore structure, or if you're using fibers, interfiber spacing, becomes really, really important. That size becomes important, so you can get proper transport. Can be. So these are different structures that people have made, different types of processes that were used, and so you can create things, in ways that if it's fibers you want, you can do that, or you can create just large porous, kind of sponge-like structures that are shown here, and there's various types of methods that are used to do that. Again, depending on the length scales or scales that you need, you would choose the appropriate method. And with materials, the biggest thing is as soon as you start kind of punching holes into your structures, so making them very porous, you might say, oh, I really want very porous, okay, 80, 90% porosity. But as soon as you start putting a lot of these holes in the structure, or even large, okay, really large holes, then you can see how the reduction in your bulk mechanical properties really starts to go down. So that's a thing you have to kind of keep in mind when you start thinking about designing your structures. How far do you want to go? What kinds of material properties do you need? So your bulk material may have really high, in this case, modulus over there, but then as soon as you make pore structures out of fibers or foams, you see what a big reduction you can get in properties. So something, again, you have to kind of consider. So, again, these tables are huge, and I'm just going to skip through that. But so there's a number of processes that you can use. And again, it depends on your composition, whether you can melt them, you can put them in organic solvents, which is fine. But all these things kind of rely on various types of those types of techniques. And so 3D printing, electrospinning, and the solvent casting, particulate leaching, those are pretty common methods. And like I said, a whole host of other ones. And so routinely, these are kind of the ones that everybody they're using. With the electrospinning, the biggest benefit here is just that you're creating fiber structure. And you have reasonable control over the fibers that are formed in terms of dimensions. And simple process, easy to build up in your lab. And I think you guys had this lab yesterday or something like that, right? Okay. So you see that, right? That goes on. And so again, benefit of this is that you can use a lot of variety, different compositions of materials, right? And you can even use natural materials, depending on what they're made of, and if you can get them maybe in water or mild acid solutions, you can spin natural materials. People will spin collagen. It doesn't stay collagen, but it'll be collagen or becomes gelatin because it will denature. But, so virtually you can spin very flexible in terms of the types of materials you can make out of this. And okay, we'll skip kind of that. And like I said, the fiber dimensions become important. So if you're trying to mimic the extracellular matrix, okay, and we're talking about collagen fiber, if your matrix is made up of collagen fibrils, fibrils may be on the order of 50 nanometers on up, single fibrils could be very small, like 50 nanometers or 100 nanometers. This imitates that. If you're looking at a collection of maybe collagen fibrils making fibers, right? Then you start to get on the order of, say, 1 micron or so. You can imitate that. So that's the neat flexibility with electrospinning, getting those different size ranges in nanoscale to microscale. If you've got some neat tissue, a lot of the extracellular matrix is organized. So those collagen fibers don't stay random. They've started to become ordered, right, in some way in certain tissues. So you can also create aligned structures easily. So you can just look at that physical feature, okay, of how does that influence cell function using this type of process. And drawback, though, is fiber spacing, okay? So conventional methods, you get control over diameters, but your spacing between fibers, you don't have a lot of control over that, right? You kind of get what you get when you make the scaffolds. Okay, and then just quickly solve these other techniques. This has been around a long time, but it has really good control over, really having a good, porosity, pore size, and all of that. And so if you really want to anchor down, I need 80% porosity, and I need like a pore size range of 200 to 300 or something like that microns. This is a good technique for that. Again, it's a solvent casting technique, so you dissolve your material into solvent with your some porogen, and that stuff gets leached out, and you can get these large structures. But these form foams or sponges. So the morphology of those structures, don't really look like natural extracellular matrix, okay, in many cases. And it's microscale features. Same thing with 3D printing. So you can get tissue structure formed, okay, which is nice. And so you can design things, and you can do fast prototyping, right, of these using 3D printers. And more of these 3D printers get developed. It's starting to become a little bit, the types of materials you can use, it's coming along, right? Before you were very limited. It's become a little bit better with some material compositions. But at least you can have a well-designed 3D structure, okay, that will come out, so you can have really defined good pore structures or structures, dimensions defined. And there's various techniques for that. Okay, so the rapid prototyping. But again, I would say, on the scale of things with processing, again, you can't print nanoscale features. So imitating the natural extracellular matrix is not really quite there. Okay. So again, kind of just to summarize and tie it up here is with the matrix and the significance of the matrix or the scaffold. And again, it's really how the cells, you're developing materials, you look at various compositions, does it give you the right chemistry, and then ultimately looking at what kind of structures do I need. And you can have things on the more micro scale, okay, but again, to really mimic the native ECM or extracellular matrix, things become smaller and smaller down, get down to the micro to nano scale. And I would call this more macro scale. And so, and again, so it's really the ability of the cell to interact with those matrices and scaffolds. And so as you get down smaller and smaller, and this may be brought up more maybe tomorrow, has already brought up, as you get down smaller in scale, you are getting a higher presentation of those features. Maybe it's proteins that are present on those fibers, higher concentration of those presented, or a higher amount of that is being presented to the cell. And so cells are more readily going to interact or attach to those micro to nanoscale features. And so that becomes very useful. Like I said, so fibers, nanoscale, even fiber structures become very useful as a model system. And that's it. Any other questions or anything about some of the things that I've covered? The take home is hopefully that, like I said, you have a better sense of some of the material compositions that are kind of out there and why people choose certain things versus others. Any other questions? Good. Okay. Thank you very much.